Good morning. Welcome to the National Archives in College Park, Maryland. I'm Robert Chaddock. I direct the research activities of the National Archives Center for Advanced Systems and Technologies. It's my privilege this morning to introduce Dr. Maria Stava from the Texas Advanced Computing Center and the University of Texas to share her perspectives and her experiences as an archivist leading a national-scale cyber infrastructure research program that is jointly supported by the National Science Foundation and the National Archives and is recognized by the President as one of the priority activities of federal research in fiscal year 2011. So with that, it's my privilege to introduce Dr. Stava. Thank you. Thank you, Maria.
Thank you very much for being here this morning. Bob Chaddock asked me to prepare a talk to share with my colleague archivists my experience and perspective working at a supercomputing center. So this morning, what I will share with you are aspects of my work at the supercomputing center, as well as the aspects of the research that I conduct for NARA at the supercomputing center. So we will talk a little bit about my role at the supercomputing center, the activities that I develop there, and then the dynamics of the research and the way in which we approach research as a member of a team with computer scientists in the context of cyber infrastructure. But so first I thought, I would like to talk to you about what is a supercomputing center. So I'm going to talk from the perspective of TAC, Texas Advanced Computing Center. It's a research and service unit at the University of Texas at Austin. Is one of more than a dozen supercomputing centers in the country. These supercomputing centers are all connected through very powerful networks, and each of them build and maintain this high-performance computing. And these are used by researchers at the University of Texas at Austin and nationwide to conduct their computational analysis. These types of analysis and these types of computations would not be possible to perform in their desktops or servers. So this infrastructure, this cyber infrastructure, is created to maintain, first of all, to design, build, and maintain these supercomputers. There are various types of resources, and each resource has a specialty, and it has an administration, and it has a maintenance that is very complex. And a lot of the research being conducted at the supercomputing center has to do with how to build, how to maintain, how to make these machines perform and conduct these jobs that enable scientific discovery, simulation, and they're mostly geared towards the sciences, engineering, astronomy, geology, environmental control, etc. Right now, there is also an opening, and the supercomputing centers are trying to open up to the humanities and also more to the social sciences. But the reality is that these computers had been at the beginning designed to tackle big simulation problems and big data problems that are found more in the hard sciences areas. So I say that it's a service and research organization because there's a community of users. These users request allocations, which is time on these machines to perform their computation, and that implies a huge organizational schema to take care of these users, consult with them, train them on how to use these resources when needed, and also debug their programs and help them run their programs. So it is a service organization. It has a user-oriented aspect to it. It also has a, I would say, external relations and PR aspect, because we are also devoted to communicate to the world and to the academic community and to society the importance of supercomputers and the discoveries and the research that they enable. The TAC specifically also conducts training and it also teaches scientific computing courses at the college, undergrad and graduate levels. Lately, and I will talk more about that, there's a push coming from the National Science Foundation that has realized that during all this time, researchers have been collecting scientific data collections. They have been gathering data, observational data. They have been gathering all these scientific data collections, and there's a need to take advantage of these scientific data collections and make them available to the rest of the research community. So within that push, TAC decided 2 years ago to open up another area that is called scientific data and collections management. And in that role and within that unit is where I was called to work at TAC. So my job description. So I am a researcher. That's my job description. I am a research associate. So I am evaluated for the research that I conduct. I work in two groups within TAC, data analysis and visualization, where I conduct research specifically for NARA at this point. And also I work in the data and collections management unit. And I will talk more about both. This is a very dynamic and evolving role, and I hope to communicate with you what this entails. So I will start with the data and collections. It's called data and collections management. So at the university and nationwide, but basically we are devoting more to collections developed at the University of Texas. There are all types of scientific data collections and others now, as I say, we're trying to get to humanities and fine arts collections as well. These scientific data collections enable other researchers should be placed to the public so that other researchers can access them. For example, there's herbarium data, there is observational data, there is imaging data, there is specimen data, and all of these huge data collections that institutions have been either digitizing or creating born digital collections need an environment, need an infrastructure that is composed of storage and databases and a management infrastructure that is very complex, and that researchers in general don't have the capabilities or the knowledge to manage the collection. So the idea is that this unit will help the researchers use infrastructure that is already maintained for them, where they can build their collections without having to worry about all of the IT aspects of maintaining the servers, maintaining the machines, repairing the machines, giving access to the collections. So they can build their collections within an architecture that is ready for them, that is maintained for them. The added value of this service is that, as I have told you, TAC has computers, supercomputers in which data analysis jobs, huge data analysis jobs, can be run. It also has visualization systems in which the collections can be displayed to the public at high resolution. And so there's a seamless communication or a seamless transition between the storage, the analysis aspect, and the visualization or display access. And this is a unique environment that enables access to the collections and enables analysis to the collections that otherwise would be very complex to carry on, especially when you talk about large data sets. But for this, the administrative model that is being used to take care of these collections is the administrative model based on supercomputing allocations. So in that way, the supercomputing center really differs from an archive or a library. This means that as scientists, as I have told you, request allocations to conduct data analysis jobs or computational jobs, in the same way they request an allocation for storage. They request an allocation to store their collections, to build a database where they can control their collections, to build web services where they can give access to the collections. But this allocation has to be renewed year by year, as much as researchers renew their allocations to the supercomputers where they run their computational analysis jobs. So from the perspective of an archive, of an archivist, is this hosting? Usually they call it hosting data collections as opposed to archiving data collections. Do we preserve for the long term, or do we replicate the collections so that we have backups of the collections, but we don't do perhaps we don't do all the rest of the preservation activities that we understand as preservation activities? Do we care about the collection's provenance, or we care about the collection's workflows, meaning not only we have to keep information about who created the collections, but also, and what the functions of the collections are, but also what are the processes through which these collections come to be. What are the scientific methods used to gather this data? What are the transformation aspects that these collections go through to become what they are, to become scientific data collections? And the service model that we are building is based on the latest requirements of NSF. So NSF has realized that all the investment in research that has been done requires that the scientific data collections that researchers build when they do and conduct research needs to be recovered for the public. So they need to make their data sets available to the public. And that is the latest request that NSF is telling the researchers that they have to incorporate in their grant proposals preventions to make their data available. And to make their data available, like we all know, we need to, that data needs to be organized, it needs to be described, just like in any other archive. And so this is the model that TAC is trying to incorporate into their services. And this is why I belong to this data collections management team. I'm sorry, I will go back. So what does this mean? So TAC has a data storage resource, it's called Corral. Corral has 1.2 petabytes of online disk. What this means, and huge network capabilities. What this means is that this data is on disk and is available to the researcher like this, as opposed to be, it's also replicated on a tape archive, but it's available to the research, and it enables to do these computations. So for example, we have data on disk that was gathered by NOAA related to the hurricane that happened in Haiti. And because the data is readily available, then scientists can make predictions and they can study this data at the moment and at the time in which the disasters are happening. It's because of this readily available data on disk, as opposed to being just on a tape, and they have to be retrieved on a tape, and they have to be analyzed in another environment. So there's a communication between the storage, the analysis, and the display environment. You probably know about IRODs. So another aspect is that this data storage resource can also work as an archive as long as the collection is stored on tax resources. And so IRODs is installed, and it allows long-term management of collections. It allows to gather and register metadata for those collections. It checks on the authenticity and integrity of the collection while we have it, for the time that we have it, at TAC. And it allows management of off-site replication and geographical replication. So we replicate all of our data at a tape system that we have at TAC, off-site, meaning on another building, but at the University of Texas campus. and then geographically at another supercomputing center. In this case, we have an agreement with Indiana University. So this means that the data, while it is attacked, is going to be safe. There is a model for the maintenance of these machines that is unbelievably efficient. I mean, the machines are constantly being refurbished and they are constantly being changed. They're being updated constantly, and so your data is secure, your data is available, and it has all the preventions, all the replication preventions, as it is stored at TAP. So, in the meantime, what did I do, or what are my roles within this infrastructure? So I designed the scientific data collections catalog. I work with two of my team members who are relational database management experts, and I studied different metadata schemas that are from, the basic doubling core schemas and mod schemas to scientific data collection schemas, and created a catalog that will not only track descriptive information about the collections, but also the scientific provenance of the collections, meaning how the data was gathered, what are the instruments that gather the data. I mean, all this contextual information that researchers will need in order to understand the scientific data collection. And it will gather events, and it will also gather technical metadata. So that was my input, creating a scientific data collections catalog that is catered to these very complex collections, and that also tracks our activities, whether we do consulting, whether we help with records management, whether we help building a database for them or a GIS database for them. So we keep track of our activities and the events of these collections. I also realized that the types of collections that we are servicing are evolving collections. So scientists really don't have, as I said, the time or the resources or the knowledge to, as they gather data, the data needs more complex systems to be able to be accessed and also to be able to make sense. So these are evolving collections. They are growing as the research project grows. And I will just tell you an example. I will just use a case study that we are working on with archaeology data. We're working with the Institute of Classical Archaeology that for many, many years they have been gathering digital data of all sorts, from GIS data to relational database management data to 3D models, to images, to digitized forms. And they had it in the institute all spread out in servers and hard drives and you name it. And so as an archivist, I was able to do a collections appraisal, guide the researchers on an inventory, capture and research documentation processes through a file naming convention and a hierarchical directory structure that will render the relationships between these data objects and also the relationships of these objects as they move on the research process from the site to their publication. Devise a file name and record keeping structure, and created a metadata mapping and integration system that allows to gather metadata from different points in the collection, from the file naming convention of the object, from a relational database management in which the archaeologists put data as they gather collections from the site, and from a record-keeping system where the original objects are being kept. And mapped all of these to doubling core schema and premise schema. And we use automated metadata extraction rules using IRODs. So the beauty of this is that as the researcher inputs or makes their data to be ingested into our IROD system, metadata is extracted from the collection structure and from all these different elements and parts, and the metadata is registered on IRODs. So then the scientists or the researchers can go and search the metadata, that they can go and search for an object, and they will retrieve an object with all of its other elements that are all connected through the code in the record naming convention. So this allows for the scientists to avoid having to write all of this metadata, because the metadata is basically extracted from, I'll show you again. As the data is ingested from, for example, if it's an image documentation, it will go to the Dublin core, in which you have the relation. If it's a type photograph, is part of, and here you have the code that corresponds to the context from which the object was retrieved, whether it was after or before conservation, etc., etc. So we gather the description from the database, and so in this way, the scientist doesn't have to, input all this metadata that is already within the file system and record keeping system. So that is a project that we are also presenting at the Digital Curation Conference in December. This automated metadata extraction using IROD's rules. So that's one aspect of my work. And I also conduct research for NARA. I am the lead of a team, but I have to say that I have a co-PI that is a computer scientist, Dr. Weijia Hu, and I will talk to you about the dynamics and what it means for an archivist to work with a computer scientist in this endeavor. And I will try to, use stories for you to understand what the process is about. So our research involves the use of visualization for archival analysis. This is use of visualization or information visualization to conduct archival processes, from appraisal to description to inferring arrangement, all the activities or some of the activities that archivists conduct normally, taking into consideration the large amounts of data that we have to process. The use of information visualization, what the goal of information visualization is to provide abstract views of the data and allow the archivist or the domain scientist to interact with the data and obtain insights from the data. As you were doing, before with paper, that you're looking at all the records and finding how the structure of the records is and describing these. The visualization intends to help and aid in these archival processes. So we try to map into the visualization principles, theoretical principles, as well as practical processes. And this research involves, as I have explained before, the use of cyber infrastructure. As I have explained before, in order to be able to analyze large amounts of data, you need these high-performance computers. You need these networks that can communicate the storage, where the records are, with the analysis processes, with the possibility to view or to interact with the data. So we are using a testbed collection, the cyber testbed collection that NARA has been gathering for research, which has, at this point, billions of files. We have worked with, so far, with 3 million files as a testbed collection to test our methods. The dynamics involved in this research, so so there's a model Yes, it's a traditional model. Computer scientists work with all sorts of domain scientists. I mean, they work with biologists, they work with chemists, they work with managers, they work with economists. And what they normally do is that they gather the requirements for the systems that they have to build. They ask the domain specialist, what do you want in your system? Then they go back, they build the system, and then they come back to you and you evaluate the system. So in a way, all the processes that are involved in building that system are detached from the domain scientist. In this case, since I work at the Supercomputing Center and I work close with the computer scientists, the dynamic is much more close. And in a way, that communication feeds each other's imagination and informs each other's. As much as I learn about the technical processes involved in building this visualization and building all the data analysis methods that need to be built within the visualization to conduct archival analysis processes, the more I can imagine new ways of visualizing records, new ways of servicing the purposes of archival processing and description and appraisal. And the more that my colleagues talk to me, the more they understand what archivists do and what are the principles that we follow. The process of research is full of uncertainty and bliss. There's a lot of decision making. You can go in many, many directions. There are always options. Uncertainty means that you decide to follow a path and you feel that you're not getting anywhere. Then there are moments of bliss, and then you keep going, and that's the process of research is like that. And you always have to make decisions. And in my case, I always try to stick. In working with records, there's a tension between what would somebody think a researcher would like to discover and what the what the archivists need in order to describe and process and make these records available. So there's always this dynamic and this dialogue. And as I said, the more we learn about each other, I consider that the better product we are going to achieve. The more I understand about the nature of electronic records, the more they understand and the potential and limitations of technology. And so I can imagine, but I can imagine without fantasizing. And the more they learn about us, about what we do. So I want to just illustrate this with a case. When we were thinking about, so that you see how things work, and it's just one example. So when we were thinking about, when we were writing a proposal, this was almost 2 years ago for NARA, we were thinking about what are the problems, what do archivists need? What are the problems? And I have always been inclined or obsessed, I guess, with unorganized and chaotic archives, such as those found in network servers that they seem unapproachable to us. There's no evident organization, there's no evident way of accessing these very, very unorganized and idiosyncratic archives. They're aggregations that people in organizations or projects deposit their records without any unified, evident intellectual control. So I thought to myself, well, if we can find the stories in the archive, if we almost can pick up one record and pick all the stories related to one activity or a transaction, we can start making sense of the archive. We can access the archive through those stories, if those stories are also related with their provenance or with their authors. But I knew, because I had used text mining before, that the difficulty with so normally in information retrieval, you measure the similarity between text documents, and so you retrieve documents that are about the same subject. You measure the word similarity between documents, and so you retrieve similar documents, and this is what happens in websites and web searches. But I knew that, we know that that records within an archive are very diverse. They are very different. Some are long, some are short. One document may contain many, many topics. It might not just talk about one activity, but about many activities. So how do you really retrieve, stories about one activity or about one transaction? So I spoke about this with my colleague, Weija, which also, he's a computational biologist, and he has worked in many RNA and DNA data projects. And I explained to him not only this, but I also talked to him about the way in which these archives are created. They're, usually very redundant. People cut and paste information, and they create records that contain bits and pieces of text from every other person. And so he said that this made him remember sequence alignment, DNA sequence alignment. And he explained me that biological sequences are made of units, biological protein units, and these units, when you align them to find the similarities, because similarity between these sequences show a structural or a functional relationship between these units. And over time, it might mean that there's an evolutionary relationship between these structures. So he said, why not, instead of measuring the similarity between two documents, a long and a short document, we measure the similarity between their paragraphs. So this would be, this is a long document, this is a short document, but there's a huge similarity between these two paragraphs, not between the rest of the paragraphs. So he said, why don't we cut the paragraphs, and we measure the similarity between the paragraphs, and based on that, we derive our similarity. We did this, and we found that this is a much more efficient method to retrieve records, documents about an activity that may contain also stories about other activities, and than normal methods that measure just similarity, global similarity between the entire documents. And we were able to identify stories, trails of text, documents belonging to a same activity. It's more efficient than just traditional similarity measures, and we are testing this now in large email collections, and we think that this will work in email collections that are also, made cut and paste, or because of the forward, they contain similar paragraphs. So we also created at that point a visualization, and as you can start seeing, the colors reflect the authors, and as you start selecting the documents and their relationships, the different stories start to get connected, and you start to see a structure, or at least small structures and small groupings of text that are related to each other. So in this way, there was this, this communication in which I talked about how archives are, how these types of archives, electronic records, are made and are created and were created using the cut and paste function, and how the redundancy, we really take advantage of the redundancy in this case and the repetition of the archive to find similar stories. So this continues. And we use the same concept or the same idea of alignment to infer the organization of records collections in a at a huge scale. So I will briefly explain we are doing visualization. So we are creating a visualization, a representation of electronic records collections. To do that representation, I have been concerned about being able to represent the structure of the records, meaning how it is organized visually. So I will just briefly explain what is it that you are seeing there. It's not an artwork. These are web pages on a website. It's extracted from the huge, I will show you then the visualization, but this is just for you to see. This would be the outer directory, and these are subdirectories within which there are other subdirectories. And I have to come close here. Within those subdirectories, records or files, are arranged, and the colors indicate the different types of records, different types of files, image files and text files. And some of them, the text files are web HTML websites. So as you see, there's a these are so structured. Each of these are a different web page, but they are so well structured, so organized that they show a very regular organization. The way that we get that image is because we use the file paths of the websites, and we use stream map visualization. We create, so the outer line, the outer border line would be one directory. Within that directory, you have another subdirectories, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 subdirectories within which you have image files and text files. So this is a representation of a very well-structured website with different web pages. So the structural metadata we gather from the file paths, and we get the file names, and I made this would be, let's say, a file path, and we have names, the names of the directories or the names of the files. We parse those file names, we remove all the extra dots and slashes and all the divisions between the words. And we analyze the words. What are those words in the file paths? And we use natural language processing tools to infer whether, for example, Washington is a location, March is a time in space. We cluster location and places, and we align them to score the similarity between all the files on a certain directory and infer whether the directory is more or less organized according to that criteria. I will show you and we render the results visually. So with this type of processing, we can help archivists infer the organization of a given group of records. We have so far explored temporal, spatial, sequence, and name alignments. There are other file names and conventions that people use to organize their data that we need to explore, such as subjects, events, names of people, etc. I will just explain you how this goes. So I told you that we aligned, instead of aligning biological sequences, we align file names. And so, for example, here we have file names that are April 2008, February 2009, December. So if we want to align word by word, we will find that we don't have a good alignment. But when the system finds out that these are sequences, it replaces the sequences, it replaces those April, February, December, June, September with signs. And so it gives us a perfect alignment. And we can infer whether this is perfectly aligned or perfectly organized by, in this case, dates, March, April, May, etc. The same happens with places. Alabama, Arizona, California, they have different lengths, the words. So when the system detects that this is a spatial name, a name corresponding to a city or to a region or to a country, it replaces it with uniform sign, and so it gives a score of how aligned these files are according to space. We also do the same with file naming conventions that have similar naming systems, and with naming conventions that have a sequential order. So I will show you a video. Here in the video you can see this is a representation of the testbed collection, the electronic records testbed collection at the National Archives that is called Cyber. Each one of these squares represents a federal agency. So there are 126 federal agencies represented, and the size of the square indicates the number of files for that collection. So the bigger the square is because the collection is big. In this case, we have also shown the second, so you know how collections are nested and there are various levels of directories and subdirectories. Here we can see the fourth level. So within these divisions, you start to see all these subdivisions which represent the subdirectories in the collection. And I will make the video go on. I will try to explain what's going on. We do a selection of a view, in this case, whether we can infer whether these subdirectories are arranged by name, by similarity within name, and the different colors of yellow represent the score, which means the range or the degree in which the alignment by name is consistent. So you can infer whether that bright yellow directory is more organized than the one that has lighter yellow. This is just we can also go to individual subdirectories. We showed first all the view of all the records collections, and now we go to the records of the Bureau of Census. And here we saw in the first view that it was all yellow, so what's within, what's underneath, summary file 1, summary file, congressional districts, it shows that there's a consistency on the file naming convention. And so you see what the directories underneath are all organized by name. Yes, it's name. It's name. And then this is another group of records, National Water Quality Assessment Program. Here you can see also that there's organized by name and what the different levels of organization are. And when we go back to see the subdirectories within, we see that we see the names of the consistency in the names of the subdirectories. This again is sequential organization. The other one was named. This is sequential organization. So when we go and see the directories underneath, we see that there's a sequential organization. And some of them can have sequential and name, both types of organization. Meaning that their names are similar, and there's a sequence. This is another example. Again, sequential. So this means that in this directory, the subdirectories underneath are organized sequentially. And here the tooltip shows what the 2002, 2003, 1999. So there's both there. In this case, there's both a sequential organization and a temporal organization. And later you will see views in which we can see two types of organizations at the same time. I am a little bit of a prisoner of this video. These general views allows you to compare and contrast between different, and to see certain patterns, and what are the main organizational schemas of the present in the collection. So in this case, we can see both temporal and spatial organization, blue and green, and both, which is gray. So here you see, for example, New England, South Plate, South Dakota, New Jersey. So all of that is a spatial organization. They're organized by a geographical location. And when the video goes and touches on the gray, it has both temporal and spatial. And so in this way, you can start to see patterns, and you can see at each level of nesting what was the criteria with which the records were organized. And the general views allow you to compare and contrast between different record groups or subgroups, and then the individual views for each record group or for each subgroup allow you to understand the criteria for that specific collection and to study more a collection in depth. And you can navigate the structure. So as you can see, the whole point was to show you how the dialogue between the archivist that understands the structure of the collection, how the collection was created, what are the characteristics of the collection, when transmitted to the computer scientist, brings up ideas on how to show or how to show and how to analyze collections at large scale. I want to say that what you see in this representation are 3 million files. Not all of them. 3 million files. Some of them conform. Some of them conform. The relationship between records and files is not 1-to-1, but this allows to get an overview and also to study in detail. At least what I'm showing today is just the organizational structure of the collection. What can be inferred. Yesterday I showed, and I am sorry seeing Anne and Doris here, I could have shown the preservation application, but it won't be shown today. So as not everything is research, I also worked on digital art displays. At the Supercomputing Center, I organized the first digital art display and curated the first digital art display at TAC. TAC has a visualization laboratory. It has the biggest tile display in the world. we used that display to display the tree map visualization at large scale so that archivists can come and look at the visualization. But I was just wanting to tell you how many things I do at the Supercomputing Center, and one was this. It was a huge event. It was a fun event. And the nice thing about it is that one of our artists, Lawrence McFarland, who just won a Guggenheim Award, decided to realize the importance of the systems and decided to request an allocation for storage of its beautiful digital art collection. So we will be preserving Lawrence McFarland's collections until, as you know, within the limitations of the Supercomputing Center, given that we are not an archive up to date. So the thoughts that I want to leave with you, is the Supercomputing Center the place for an archivist, given the, given the limitations of what is considered hosting collections? I think that all of the archival theory, the observations and the processes that I have learned in my training are fundamental to my job, are fundamental to my work, that they remain intact. I just think that maybe the methods with which we process archives, with which we describe archives, and we plan for their long-term preservation have changed. And we need to look into, large scale and how to synthesize the information so that we can make sense of large collections as opposed to working with discretely. And this, my work in that institution being so dynamic and so flexible and makes me think about what are the archiving models of the future, what are the access models of the future, what will researchers in the future need when they have to access these large, huge digital collections, how are their modes of research changing our modes of service. And basically I have reflected a lot on understanding more the nature of digital objects and therefore the nature of digital records, although I am still thinking how I can separate conceptually these two aspects. So this is what I finished, and I will welcome any questions that you may have.
Thank you, Dr. Stava. Thank you. Thank you all for joining us this morning. As we conclude, one of the things I would observe is basically one of the privileges we have of hosting Dr. Stava is the aspects of presenting a research that is informed by her perceptions as an archivist. And it's my privilege to host you, so thank you.